So, thanks a lot.
Great, thank you. So the idea of this talk, I want to start by telling you kind of the conjectural picture of what's supposed to happen in percolation at the phase transition on cubic grids and things like that. This seems very hard. There's lots of open problems. We don't really know how to do very much. And then I'll tell you about some other models that are closely related and are supposed to exhibit a lot of the same phenomena and be very similar in various ways, but are actually significantly easier to study, and we can actually prove some of these things about them. So let's just start with just a quick overview of Bernoulli bond percolation. So we have a graph, which usually I'll take to be ZD, the hypercubic lattice, dimension D. Okay, and we have delete or retain each edge independently with retention probability P. Okay, where P is a parameter, it ranges between 0 and 1. So you're just doing all these independent coin tosses. Everywhere you see a head, you keep the edge. Everywhere you see a tails, you delete the edge. Okay, and the standard jargon of the field is that the deleted edges are called closed, and the retained edges are called open. Okay, and generally speaking, what you're interested in percolation is the geometry of the random subgraph that you get by doing this. And in particular, how this geometry depends on this parameter P. Okay, so the kind of first basic theorem about the model, which I'm not completely sure who it's due to be honest, but in spirit, it's due to Piles, who did something similar for the Ising model, is that in dimension at least 2, there is a phase transition. Which means that if you define PC, so this is a function of the graph, to be the infemal value of P such that an infinite, so another piece of jargon is that the connected components of this random graph are called clusters. So PC is defined to be the infemal value of P where an infinite cluster exists with a positive probability. In fact, by Komogorov 0-1 law, this is a 0-1 event, so when it has positive probability, it has probability 1. And so the theorem is that this is strictly between 0 and 1. In dimension at least 2. So dimension 1 is not interesting. PC is equal to 1 as soon as you delete any edges. You're never going to have an infinite cluster left. But in higher dimensions, once you retain a sufficiently high density of edges, you will be left with an infinite cluster. Okay, so this is really just the starting point of the study of percolation. And a lot of the most interesting questions pertain to what happens, at this phase transition. So that might mean taking P to be exactly equal to PC. There are also lots of interesting questions about just taking P very close to PC, which are typically harder actually. But generally, there's a lot of interesting stuff that goes on at and near this phase transition. Okay, now, one of the most basic problems is that, well, we define PC to be, this infemal value where we have a positive probability, but of course that doesn't tell us whether the probability of having an infinite cluster is 0 or 1 at PC itself, right? And so one of the big kind of conjectures in the area is that at PC, you should never have an infinite cluster in every dimension above 2. So this is now known in 2 dimensions. It's been known like since the 80s. It was proven by Harry Keston. And in very high dimensions, it's been understood since like the 90s by Hara and Slade. And I'll say more about that in a second. The record at the moment is like D at least 11, and that's like a computer-assisted proof, like optimizing the numerics to get the dimension down as much as possible. But that proof actually, the whole strategy it's based on can only possibly work up to 7 dimensions. And in dimension 3, 4, 5, and 6, it's expected that something totally different is needed. Of course, 3 is the most interesting dimension physically, and we really have no idea how to understand these problems. Okay, now, really though, this question about the continuity, so that for this problem of whether you have infinite clusters at the critical probability or not is often called the continuity of the phase transition. One reason is that it's equivalent to, if you look at the density of the infinite cluster, it's whether that density is continuous in P or whether it has a jump discontinuity at PC. So this question about continuity of the phase transition is really like the first step that we would like to understand, and then there's a huge world of like more quantitative things that we would really like to understand. So in particular, we expect that percolation, as with other models of statistical mechanics, has a lot of really rich and interesting behavior happening when you're exactly at PC. So for example, if you look at a big box, there'll be kind of big clusters of all different sizes. And if you look at one of these big clusters, it should have a kind of interesting fractal-like geometry. And this is, again, something that's fairly well understood in 2 dimensions, in high dimensions, but not in intermediate dimensions. And one of the ways we understand this kind of fractal geometry of the critical percolation clusters mathematically is in terms of critical exponents. So basically, the idea is that various quantities of interest should have some kind of power law growth or power law decay. Okay, so I'm just going to focus on 2 of them, which is that, so K is my notation for cluster of the origin. And it's expected that this should decay like a power of acriticality, the probability the cluster of the origin is large. And for somewhat mysterious historical reasons, this power is denoted like this. Okay. Another exponent is that if you look at the probability that 2 points are connected to each other, i.e. there's a path of open edges connecting X to Y, this is also supposed to have a power law decay. And the traditional way to write this is like this. Okay, you'll see why this is a reasonable way to write this in a second. So, part of the conjecture is that these things have power law decays, right? But there's 2 difficult things going on here. You have to both prove that you have power law decay and compute the exponent at which the decay holds with. In fact, usually it's very hard to do the first one without doing the second one. Like abstract proofs that you have power law decay without a computation of the exponent are very rare. Okay, so these kind of things are fairly, so maybe another point is that these exponents are supposed to depend on the dimension of the model in an interesting way, which I'll come to, but they're supposed to be independent of the details aside from the dimension. So for example, if you look at the square or the triangular lattice, you expect to get the same values of these critical exponents. If you do side percolation instead of bond percolation, you should get the same critical exponents and so on. So they're supposed to be insensitive to the details, but sensitive to the dimension. So what happens is that, or conjecturally at least, is that once you go to sufficiently high dimensions, so I'll write these as conjectures. Some pieces of this are actually theorems, but overall this will be a bunch of conjectures. So first there's the high dimensional case, which it turns out for quite subtle reasons that I probably won't have time to go into. High dimensions for percolation means strictly larger than 6. You get what are called mean field critical behavior. So essentially what mean field behavior means is that once you go to high enough dimensions, the model kind of stops feeling that it's in a finite dimensional setting, and it starts kind of behaving like it would in some kind of infinite dimensional setting, or in other words, some kind of geometrically trivial setting. So one way of thinking about it is that percolation behaves kind of the same way on sufficiently high dimensional lattices as it would on like a binary tree or a complete graph, or something where you don't really have interesting geometry. Okay. A slightly better way of thinking about it is that percolation in high dimensions behaves like branching random walk, which is a kind of a much simpler model. Okay, so concretely, two things that happen is that if you look at the probability at criticality, that you have a large cluster at the origin, this decays like 1 over square root n. Okay, this means that there are upper and lower bounds with constants where the constants can differ in the upper and the lower. Okay, so this is the same as if you take a critical branching process with finite variance. It also has this 1 over root n tail for its total progeny. Okay, and for this guy, by the way, this is called the 2-point function. I better just mention it now because I'll probably call it that and you'll have no idea what I'm talking about. This is just this name for the connection probability between 2 points. So, and the 2-point function decays like the Green's function. In other words, delta is 2 and eta is 0. Okay, so again, these are the same exponents as you get for branching random walk. Okay, now, as I said before, you know, the continuity problem has been solved in high dimensions, and the solution to this, which is based on something called the lace expansion, it really establishes all this strong stuff. And it doesn't just prove continuity, it proves like that you have mean field behavior. And because we only expect this behavior to hold down to 6 dimensions, we kind of know this technique cannot possibly work in lower dimensions. Okay. So for d strictly less than 6, we expect that these exponents take different values, right? That they're not the same. So in other words, in low enough dimensions, the model really starts feeling that it's not in this infinite dimensional trivial thing, it starts feeling the finite dimensional nature, and the exponents change in some very subtle way that we don't really know how to understand, but it depends on the dimension. Okay, now the one case that we do understand fairly well is 2 dimensions, where these things have been exactly computed. First of all, there were predictions from physicists using conformal field theory and stuff like that by Nienhuis. And then, you know, this has actually been proven rigorously, at least in some cases. So it's like, this is something I hope to be solved. Notes for delta is 91 over 5. And eta is 5 over 24. So, and this is kind of characteristic of these 2-dimensional things, that you get these kind of complicated rational numbers coming out. And this is to do with the fact that it's connected to conformal field theory, which has lots of connections to algebra, and you know there are interesting algebraic things underlying these. Okay. Now, in contrast, in say 3, 4, and 5 dimensions, even at a heuristic level, even physicists have no idea how to compute what these exponents are, and there's no particular reason to expect that they have, you know, exact forms that you can write down, you know, even in terms of pi or whatever, right? I mean, there's no particular reason to believe there's any simpler description of these than that they are the critical exponents of these models in some sense. Okay. Now, the 6-dimensional case is also interesting. So 6 dimensions is like, so it's what's called the upper critical dimension. So it's exactly at the boundary of when this mean field behavior starts holding. And I should say this whole story, you know, the particular values of the exponents and so on are particular to percolation. The fact that 6 is the upper critical dimension is particular to percolation. But the general story that you have an upper critical dimension above which you have mean field behavior, and then it changes, happens for, you know, lots and lots of models in statistical mechanics. So at d equals 6, what you expect to happen is that this mean field scaling does not quite hold, but it only differs from mean field scaling by logarithmic factors. So the conjecture, so I mean, this is really, the authors didn't phrase it as a conjecture, right? This is a physics paper. It's a prediction, I suppose. From 78, says that in 6 dimensions, the probability you have a large cluster. So you get the same n to the -1/2 as in high dimensions, but you have to multiply by log n to the 2/7. Okay, and if you look at this, let me just do that instead of writing it in. If you look at the 2-point function, you're supposed to have, again, the kind of main thing will be this Green's function term that you get in high dimensions, but you have to multiply by a log correction, which is 1/21. Okay. Of course, log to the power 1/21 is a pretty slow-growing function, but nevertheless, that's the conjecture about what happens. Okay, and you know, although from the physics perspective, this has kind of been like a settled thing for a while, this still is very much beyond what we can actually prove as mathematicians.
Do you believe them?
Do I believe it? Yeah, I think so. You know, there was a point earlier this year where I didn't believe it for reasons that will become apparent later on in the talk. But there are a bunch of steps in the, there are some that are like standard, okay, these are like heuristic physics arguments that we kind of know work, even though they're very hard to implement rigorously. And there are other steps that are kind of like, well, like one thing they do is that this is based on the renormalization group. And the thing is the renormalization group is really something for spin systems. It's like where you have like fields. Percolation doesn't fit into this context. So what they do, one thing you can do to get percolation in that context is you can say, well, there's the Potts model and the Ising model that have this parameter Q, and you can try to compute the exponents for those, which are spin systems. And then at the end, like as a function of Q, and then set Q to 1 when you're done. Okay, which is probably does give you the correct answer, but it's, you know, it's very far away from being any kind of rigorous argument. Yeah, anyway. So another interesting thing is that, you know, as I said, even physicists don't know how to compute things exactly in this low dimensional case. So, so there was this idea of Ken Wilson, who's the kind of the founder of this whole theory of the renormalization group, you know, Nobel Prize winning physicist. And one of his ideas was that, okay, low dimensional things are very hard to understand. So what we'll do instead is, instead of looking at like 3 dimensions, we'll say, suppose D is 6 minus epsilon, and then try to like expand the exponents as powers of epsilon. Okay, so physicists do this. This is a big industry. It's really hard, and it's not like, you know, if you get one more term in the expansion, that's a paper. You know, it's a good paper. It's not like you can expand to infinite order. It's not like you expect these series to converge anyway, even if you could expand them to infinite order. You know, this whole thing is riddled with things that, as mathematicians, are very scary. Nevertheless, it turns out, you know, at the end, you set epsilon equals 3, and you get something that has pretty good agreement with numerics. So, so for example, you know, if you read the physics literature, and there's a Wikipedia page about percolation critical exponents that's very good for this kind of stuff. You get this expansion, supposedly, and there's a similar one for eta. Okay, now, you know, one thing is that these like I said, there's not even like an algorithm that will like produce what these coefficients are for you. So the whole thing is horrible. Of course, you know, as a mathematician, the first thing in your mind though is that, oh, this is just nonsense, right? Like I can't do a model in 6 minus epsilon dimensions. Like, okay, but actually, although this seems like the worst thing about this picture, as a mathematician, this is actually the easiest thing to deal with. And so the usual way this is done is by moving to a slightly different setting where we have something that is analogous to the dimension, but which it does now make sense to vary continuously. Okay. So the way to do this is with long-range models. This is long-range population. Okay, so the idea is we're going to start with the d-dimensional integer lattice as before, but now no edges. There's not going to be any special role for nearest neighbors. Okay, and what we say is each xy, so any pair of vertices could be an edge, and it is an edge. Well, let's just say it's open. It becomes an edge of the percolated graph with prob 1 minus e to the minus beta. I'll explain this in a second. Minus d minus alpha. Okay, so where we think of alpha is fixed and beta is our like parameter.
What is alpha?
What's that?
What is alpha?
It's a number. It's positive.
Oh. Does anything depend on it? Oh.
Yeah. So this particular form is not very important. It's just convenient. The point is that for x and y that are distant, this is like the distance to the minus d minus alpha. Okay, this is just a convenient way of making this between 0 and 1. Okay. So the point is that the smaller alpha it is, the easier it is to have very long edges, and the larger it is, the harder it is to have very long edges. Okay. So the interesting thing is that the parameter alpha now makes complete sense to vary continuously, but it turns out that varying alpha is very similar to varying the dimension in various ways. But now we can do it continuously. So of course, this is not the only reason to study long-range percolation. The long-range models are just interesting in their own right. But it's particular, like if you dream of implementing any of this picture rigorously, it's kind of like going through long-range models seems to be the main way to do that. Okay. So there's a surprise. So like I said, the varying alpha is a bit like varying the dimension, and small alpha is kind of like high dimensions. Okay. And there's a surprisingly simple prediction for how these exponents depend on alpha. So first of all, of course, now I have beta instead of p. So, I define beta c analogously. So it's like the infimal value of beta such that there exists with positive probability. So of course, this beta c depends on d and on alpha. Okay. The analog of PC being less than 1 is that beta c is finite. And the basic theorem about this, which I think is really goes back to some work of Freeman Dyson in the 60s, is that beta c is finite when d is less than 2 or d equals 1 and alpha less than or equal to 1. Okay. So, in most settings, apart from this d equals 1 large alpha case, we will have a phase transition. And that when is an if and only if. So you can look at these same exponents as before. And as I said, there's a surprisingly simple prediction.
Sorry, less than or equal to 2?
Sorry. Yeah. So let's start by looking at this exponent eta. So, which was describing the decay of the connection probabilities. Okay. Now the idea is that if alpha is really big, if it's very hard to make these really long edges, then the model should behave the same in some sense as nearest neighbor percolation. Okay, so it's plausible that for some very large alpha, you really get the same large scale behavior, and and the exponent should be the same. Okay, so this is part of the prediction, is that when alpha is sufficiently large, this exponent stabilizes at whatever its nearest neighbor value is. So that just means that d-dimensional nearest neighbor value for the same exponent. Okay. Now, on the other hand, when alpha is really small, so small alpha turns out to be analogous to having high dimension, right? So no matter what dimension you start with, if you take alpha to be very close to 0, it's going to be like you're in a very high dimension. And in particular, that means that percolation should behave like branching random walk, okay? Except it's not going to be the usual nearest neighbor random walk. It's going to be this long range random walk that can take big jumps, right? So that means if you look at this 2-point function, instead of decaying like the Green's function for Brownian motion, it should decay like the Green's function for the appropriate Levy process, okay? So it turns out that what this is very simple. It's just the straight line of slope 1. Okay, that's the correct exponent for this Levy process Green's function. Okay, now what the physicists tell us in work that is from the 70s again. So mathematicians were always playing catch up on a 50-year delay or something. But what they tell us is that in fact these are the only 2 regimes. So in other words, you just keep drawing this straight line until it hits this level, and then you draw a horizontal line, and that's what the exponent is. Okay? Again, this is really just conjectural. Okay? Now, of course, this leads to a special value coming up here, which is called the crossover value, which is where you switch from this straight line to this flat line. Okay? And if you look exactly at the critical value, you expect to get kind of logarithmic corrections and so on, like similar to the upper critical dimension. Okay. So the way, at least I've come to understand this, is that there are kind of 2 ways that you might like grow a large cluster as you go up scale. So if you imagine like, you're going to have some kind of big clusters, let's say on this rectangle that's like 2n by n. And you say like, how is that big cluster in the rectangle formed in terms of the big clusters in these squares, right? So there are 2 kind of natural strategies for how you might grow things. You might say you start with a big cluster here and a big cluster here, and you grow them by like bulk to bulk, like long edge connections, right? Another natural strategy is maybe you have a big cluster here and it like touches the boundary or near the boundary in a lot of places. And then in this box, you have a cluster that touches near the boundary in a lot of places, and they grow primarily through these short connections. So I think the way to understand this conjecture is that you have a phase where this strategy wins, which is this one, and you have a phase where this strategy wins, which is this one. And up to that, that's the only thing that can happen, except possibly at this critical value where things can get wildly complicated, possibly. That's a very heuristic picture, but I think that's the way to understand this conjecture. Okay. So before I move on to the new things, and so a lot of what I've been working on over the last few years is trying to prove at least some like pieces of this picture. So before I talk about those new results, though, let me just mention that one of the nice things about these long-range models is that surprisingly, they probably seem more complicated than nearest neighbor models, but they're actually significantly better understood, at least when alpha is sufficiently small. So in particular, there's a theorem of Nürnberger from like the early 2000s, like 2002 maybe, where he proved that if alpha is less than d, then there are no infinite clusters at beta c. Okay, so this is something, as I said, that like for 3-dimensional nearest neighbor models, we have like no idea how to do this. But according to this picture, it turns out alpha c is always very close to 2. This actually includes models that are like conjecturally in the same universality class as nearest neighbor percolation in 3 dimensions. So it's kind of, and this is not so hard to prove either. It's somehow the fact that you're dealing with the long range model seems to make the problem significantly easier than in the nearest neighbor case. Okay, and this is actually So what's expected to happen is that for D at least 2, that you should always have a continuous phase transition no matter what alpha is, although that gets hard again. But in general, this is best possible because it's the theorem of Weisen-Newman from the 80s that if D equals alpha equals 1, you get infinite cluster at beta C. So in this case, remember, like if alpha was bigger than 1, you actually don't get a phase transition. So there's an interesting way where like this discontinuous phase transition is like somehow very close to not having a phase transition at all. But anyway, this means in particular that in general you can't improve this theorem. I should say, this theorem is also a big obstacle to all these problems about percolation, because if you want to prove that that you don't have infinite clusters at PC, you need to make sure that whatever your strategy is, it's not going to apply to this example, which actually rules out a lot of things that one might try. Okay. So the main thing I want to tell you about today is a slightly different setting in which we can now, completely understand a lot of these things, which is long-range percolation on the hierarchical lattice. So basically, the idea of studying these hierarchical models is, so this is something physicists have known about for a long time. And basically, the hierarchical models exhibit a lot of the same kind of phenomena and dimension dependence and so on that we're interested in studying in Euclidean space, but they have a lot more symmetry. And this like really extreme amount of symmetry is really, really helpful for studying things. I should say that the hierarchical lattice, I won't define it this way, but it's kind of like the discrete version of the p-adics. So like, that's another way of thinking about them, which I won't say, like that, it's kind of like ZD sits inside RD, right? Like a similar thing with the hierarchical lattice is like the discrete structure sitting inside the p-adics. But you don't need to know anything about p-adics. So let me just give a formal definition that probably won't be hugely enlightening. So it's going to have two parameters, the dimension, which is like the important one, and then there's this kind of extra degree of freedom, which is like choosing P in the p-adics, which is called L. So this is going to be defined as an infinite direct sum of copies of the side length L torus in D dimensions. So in other words, these are infinite strings where xi is in the torus for I, and xj eventually 0. It's finitely supported. Okay. This viewpoint on them as a group is not hugely important, but the fact that they're an abelian group means that if you so wish, you can do like Fourier analysis and things like that in this setting. The more important thing is the metric structure. So we define the distance between x and y, which we denote like this, in the following way. I'll explain what this means. We also have to just make it 0 on the, sorry, when they're the same. The formula would give 1 when they're the same. It's just slightly annoying. Just make it a metric. Where this quantity, well, let's say h of x, is just the minimum I such that hxj is equal to 0 for all j. So in other words, again, this is, I feel like it's good to have a formal definition, but let's just unpack what this means. It basically means if you have two elements of this space are these strings that are eventually zero, and the distance between them is like exponential in the first place, after which they agree for all time. Okay, so I think the following like graphical example is much better. So one way you can picture H22 is you start with the points on the square grid, and then you pick a dyadic decomposition of the points. So, first you partition them into 2 by 2 squares, and then you partition those further, into 4 by 4 squares and so on. And then the distance between 2 points is equal to the side length of the smallest one of these distinguished blocks that contains both points. Okay, so you can see that, okay, we kind of forgot the algebraic structure that was here, but as I said, that's not very important. As metric spaces, these two definitions are equivalent. Okay. So as I said, it's not apparent from this way of drawing it, but this space has way more symmetry than Euclidean space does. So for example, if I just pick these 2 points and swap them, that's an isometry of the space, right? The better way to think about it is that, you can define you have this sequence of scales, right? And to get the hierarchical lattice at scale n+1, in other words, to construct the ball of radius L to the n+1, you just take like L to the D copies of the thing at the previous scale, and then you set all the distances between points that are in different copies to be the same, right? So this has a huge amount of symmetry. In particular, so this long-range percolation thing that we defined before, notice that this doesn't really have anything to do with ZD being a graph, right? This is well defined for any metric space, okay? So we can take the same definition and run it in the hierarchical setting. Everything makes total sense, yep?
Should you erase the H in that definition of H?
Yes, sorry. Thanks. Yeah, that was probably really confusing. So we can define percolation on the hierarchical lattice, just using the same definition. And the nice thing is that when you go up a scale, no matter which 2 points you pick, as long as they're in different copies, they have exactly the same probability of being joined by an edge when you go up a scale. Okay, so another way you can think about the hierarchical percolation model is that you put like an Erdős-Renyi graph on each ball that has where P decays depending on how big the ball is, right? So you start with individual points. Okay, there the Erdős-Renyi graph is kind of trivial, and then you go up a scale and you have an Erdős-Renyi graph at this scale 1, where all the distances are the same. Then you go up a scale and you have all these Erdős-Renyi graphs you included in from the smaller scale, plus a weaker one that you add in on the next scale. Right? And you just keep doing that up to infinity. Okay. So, okay. And the other thing is that, I was explaining before how in this setup, the way to understand it is that, you have this bulk-to-bulk dominated regime and the boundary-to-boundary dominated regime. In the hierarchical case, there is no boundary, right? Like when you take 2 boxes next to each other, all the points in here have the same distance from all the points in here, right? So this strategy doesn't exist anymore. And so, from what I've told you, it's reasonable to expect that you only see this part of the graph. And this is in fact exactly what happens. So this is the first case where we really have completely pinned down. So this is on the hierarchical lattice. The critical 2-point function is up to constants given by the distance to the minus d plus alpha, which just means that this graph is just this straight line. Good. So one consequence of this, I guess I don't have time to get into why, but it's easy from known things to deduce that from this, that when d is smaller than, when alpha is smaller than d over 3, you get mean field critical behavior. Okay, there's something called the triangle condition, which is a sufficient condition for mean field critical behavior. You just have to check that some sum converges, and once you have this, it's easy to check that that's true. So one corollary that's easy from this is that you have mean field critical behavior when alpha is smaller than d over 3. Okay, now it turns out that's actually sharp. So in more recent work, what I've now been able to do, this is actually not on the archive yet, but hopefully soon. So again, this is hierarchical. Is also determining the scaling of the tail of the volume. Okay, so here we're really going to see all these three things: the high dimensional, the low dimensional, and the medium dimensional. The theorem says if you look at the probability the cluster at the origin is at least n, then, okay, there's first the high dimensional case, which is less interesting, where we get this 1 over square root n, like a branching process. And then what happens at the critical dimension is we get log n to the 1/4. Okay, and then below the critical dimension, we get a different exponent, d minus alpha over d plus alpha. Okay, where, notice that from this it's clear the critical dimension is 3 alpha, it depends on what alpha is. Okay, so, someone asked earlier whether I believed the physics, the SM Gaunt and Gutman conjecture. And, when I proved this and I got a different power of log, I really thought maybe it was wrong, because the interesting thing is that there's a small number of models where we've been able to rigorously understand these log corrections at the upper critical dimension. So one of them is what's called weakly self-avoiding walk. There's also something called the phi-4 model. Anyway, it's not really important what they are. But in those small number of examples that we do know how to understand, and this is mostly something that's been done by Roland Bauerschmidt, David Bridges, and Gordon Slade, it turns out that the Euclidean and the hierarchical things always give you the same answer in those cases that we've previously been able to understand. And this is important because essentially the way their proofs work is they first study the hierarchical case, which is already hard, and then they push that with a huge amount of very technical work. How do you force that to work on ZD instead of on the hierarchical lattice? So, the fact that you get something different in percolation is, well, first of all, I thought maybe the physics thing was wrong, which, as a mathematician, it's your dream to do that, right? Unfortunately, I spoke to Roland Bauerschmidt about it a few weeks ago, and he kind of convinced me that there are some situations in which you don't get the same thing on the hierarchical and Euclidean lattice, and presumably we're just in one of those situations. So probably the physicists are right. Nevertheless, it's interesting that you get something different. It's still something we need to understand more thoroughly. And it also suggests that getting these things to work in the Euclidean case is going to be even harder than it has been for other models. I mean, there's something difficult, even more difficult than usual going on there.
I think the power you said was 2/7. That's kind of close to a quarter.
Yeah, it is close. It's I think the difference is 1 over 28.
Yes.
And so log to the 1 over 28, it's also something that would be very hard to see in a simulation. Computing these powers of log in computer simulations is, well, it's already very difficult, even if you just want to distinguish a quarter and a half. But in particular, distinguishing a quarter and 2/7 is very hard.
But this stops at alpha, right? In this theorem. If it is less than 3 alpha, it should be bigger than or equal to 12. Or it is.
I think for once I put all my inequalities the right way around. This is the high dimensional case. This is the critical dimension. This is the low dimensional case.
Well, d is less than alpha, right? You have n to a positive power, that is
You mean here?
Yes.
Yeah, but d is less than 3 alpha.
Well, what if it's less than alpha? What if it is 0? Yes. Lower bound of alpha or something. No?
Yeah, I think, okay, it's really, the way I normally do it is alpha is bigger than d over 3, but it should also be smaller than d.
Okay.
Yeah, it's when alpha is bigger than or equal to d in the hierarchical context, you just don't get a phase transition anymore. So you kind of have to impose this for the thing to even make sense.
So because the exponent at the end could be negative. And then
Yeah.
Probably.
Yeah, indeed. Yeah, I mean, the fact that it's 0 when alpha is equal to d is closely related to this fact that you get this discontinuous phase transition in the Euclidean model. It turns out in the hierarchical one, you just don't get a phase transition. So, I was hoping to have time to tell you something about the proofs of these things. Seems like that's probably not going to happen. So maybe I'll end by telling you that, so this result gives us a fairly complete picture of at least some aspects of the hierarchical model in all different dimensions. But of course, what would be really nice would be to try to understand like some of these things on the Euclidean long-range model, right? And here we have been able to do some things. So of course, the full conjecture still seems really hard to understand. And one reason why it's really hard to understand is like even just understanding the nearest neighbor model or what this is really hard, right? But we have been able to establish parts of this. So mostly just in this setting of understanding this 2-point function, which turns out to be much easier than the other aspects of the model. Partly because there's just no dependence on, it doesn't matter whether you're in the high dimensional or low dimensional setting. So what I proved is that in the Euclidean, for long-range percolation on ZD, if you look at if you look at the average of the 2-point function on a box, this is bounded by a constant times n to the minus d plus f. Okay, so what this means is that, i.e. 2 minus eta is at most alpha if it's well defined. Okay, so in other words, in this picture, what this means is that, so conjecturally we have this straight line bit followed by this horizontal line, and this theorem says that the exponent is always bounded below this straight line, which is of course consistent with the conjecture. Okay, now a few months after this, there was a nice paper by Baumler and Berger, which gives the lower bound, the same one, matching for alpha at most 1. Okay, in any dimension. So in other words, you have this lower bound, the upper bound, and a lower bound like this. So they actually prove this lower bound past alpha equals 1 as well. So I think this is really nice. So in particular, in one dimension, alpha between 0 and 1 is the only place where you get a phase transition anyway. And so actually these theorems together actually just compute exactly what this exponent is for the whole range of relevant values of alpha. There is this annoying caveat that you have to average. And for some purposes, like trying to get further information from this averaging is a bit too much. So, one, I think, really interesting problem would just be to at least slightly reduce how much averaging is going on. Like one nice thing would be to look at the Fourier transform, which still has a lot of averaging, but it's a bit less severe. Anyway, and even in the 2-dimensional case, so the mean field behavior kicks in the 2D case when alpha is smaller than 2/3. So in 2D, you get this regime where you're not mean field anymore, but where we can still exactly understand at least one exponent. Okay, so I think this is really interesting. I would have liked to have said more about the proofs, but I guess that won't be possible. There's a lot of directions for future research. Like, one thing is that, the really nice thing would be to understand like scaling limits. That seems very hard, particularly in the slow dimensional case, but on the other hand, while it seems hard, it doesn't seem impossible. So trying to say anything about scaling limits of, for example, 3D percolation just seems like totally beyond the realm of anything we can do. But in the hierarchical case, these things can be nicer. They're not easy, but they're like you can start to build strategies about how you might study them. So I think I'll stop there and thanks for your attention.